Hola, bienvenidos a la Facultad de Arquitectura y UFM Design, donde coexistimos arquitectura, diseño de interiores, diseño de producto y diseño digital. Siempre los invitamos a enterarse de lo que hacemos en Instagram o a escribirnos a ufmdesign@ufm.edu o seguirnos en Facebook, donde estamos ahora en vivo. Hoy tengo el gusto de presentar esta conferencia del área de diseño de producto. El título es el bambú, el material del futuro, donde aprenderemos cómo materiales ligeros, biológicos y bioinspirados pueden ser combinados con novedosas tecnologías digitales. Será impartida por Jonas Hauptman, profesor auxiliar de diseño industrial, director del Laboratorio de Materiales y Diseño y miembro del Creativity, Arts and Technology en la Escuela de Arquitectura y Diseño de Virginia Tech. La conferencia será en inglés, por lo que terminaré de presentarlo en inglés. Jonas Hauptman's work is focused on reshaping the ways that we design and manufacture products and buildings. His work interweaves novel digital technologies with lightweight, biological, and bio-inspired materials toward intelligent responses to human needs. All this to generate positive ecological impacts. His current research focuses on and around bamboo, developing building scale systems that rely on generative design. So with this, Jonas, I pass you the floor.
Thank you so much for having me today, everyone. It's the first time I've been with you all and not been in Guatemala, so it's nice to be in touch, and hopefully we are all traveling again soon. So I'm just going to share some slides about my research, and I'm happy to take questions throughout the talk or at the end.
Thank you.
Feel free to interrupt. I don't mind at all. In fact, I prefer it.
All right.
So can everyone see my screen?
Yes.
Okay. So I'm the kind of co-director of a new center we've started at Virginia Tech, the Center for Biodesign Research. And I'm going to share some work largely about bamboo, but more importantly about, an ecocentric view of the world and of material. So the projects that I'm going to share, the lab itself is really a collaboration with multiple people, some from Virginia Tech, others from UVA, and some even from UC San Diego, as well as some collaborators from Guatemala and from Vietnam. And so here's just a list of sort of who's involved in our work. And I should just point out, Alfredo Maul and Roberto Banacchi are both Chapines, and we're invested in trying to work together in developing some bamboo building projects in Guate. So the lecture will kind of cover my background, the context for our work, some lab projects, and next steps. So some background. Essentially, I'm actually trained as a sculptor and a craftsman. And these are a series of businesses and projects and research that I've been involved in. One is a lighting company developing mass customized lighting that used robotic bending machines called Rumio. The second, Sion, an architectural folded plastic system to deliver kind of unique interior experiences out of luminous, lightweight plastics. I also did some work as research in California and then University of Michigan, compositing palm foliage from the LA dump, and then also developing the Reseat chair line as a company. And we produced a few hundred chairs over the first year. Long story. And then I've also made kind of artwork in collaboration with artists. This is a project in Joshua Tree with an artist named Andrea Zattel. And then finally, I used to teach architecture when I was first actually engaged at UFM many years ago. Now, I was faculty at Michigan, and we developed this solar house, which I spoke about. It's probably been more than a decade now, I guess. So my work has really, in many ways, always been engaged in thinking about sustainability. But I think my opinion about what that means continues to evolve and change. And the word equity continues to come more and more to my mind, meaning, to all people, to all sentient beings, and to all perhaps elements of our environment, how can we be part of a symbiotic and equitable system? And so I'd like to replace the notion that design should be human-centered, which I now believe to be actually quite a selfish idea, with the idea that it should be eco-centered, which does not ignore humans, but it doesn't place us at the top of some system. It places us in a loop or in a pool with lots of other elements, all of which are necessary for us to sustain life, and many of which we might help sustain life in the same process. So when I came to Virginia Tech, I was asked to teach a materials and process course as one of my major teaching obligations. And I don't love to give lectures, which you'll probably figure out today. But I also was really troubled by this notion. Historically, I had taught mostly in architecture and industrial design. I was concerned that I would really have to focus on plastics, on materials that I would characterize as being difficult within an environmental perspective. But as I kind of thought about it more, I sort of looked back at some of my older work and thought, well, maybe I can teach about grasses instead of wood. And maybe instead of just plastics, I can find some bioplastics. And it sort of led me to rethinking how I was seeing materials in the first place. And so this project is actually one from much earlier. It's from around 15 years ago, I guess. I kind of forget the year now, but I was researching palm foliage in the LA waste system, and I developed this stool. And when I started teaching at Virginia Tech, I came back to this project, which I've done with many of my sort of interests, whether it's folding or computation or materiality throughout my career. And I thought, I should think more about grasses. And so that led me kind of back to grasses and then to bamboo. And so what I came to learn about bamboo, which I find quite important and quite fascinating, is that bamboo is largely an agricultural product. It's not to say that it doesn't grow in the wild in a forest, but when it's used as an industrial material, it should absolutely be farmed, and it commonly is farmed. And so that gives us a unique position to have a forest product that actually can be farmed in a responsible way. Part of what makes it so easy to be responsible is it uses not a whole lot of water, doesn't need lots of pesticides, and also it's rhizomatic, meaning that it generates new growth from the same root structure. If you clip 1/3 of the poles every year after the grove is reasonably mature, it continues to regenerate, and most species will regenerate for 60 to 100 years. This is a really unique part about this plant that's not true about trees. Then when we compare it to trees, whether it's softwood trees or hardwood trees, the rate of growth, the rate of mature is significantly faster. As you can see here, between 6 and 10 times faster. And then finally, biology has given us such an amazing structure. The structure of the bamboo pole, if you think about it as a beam or a system, it has nodes and internodes, these diaphragms that create a really smart structure. The kinds of structures that we see humans trying to make other ways. And this naturally occurs as this plant grew taller and taller through evolution, having to withstand the wind. Not only is it got a great system, the system's even unique. There are parts of the bamboo pole that are stronger than other parts, that can take more bending stress than other parts. And that's because when the pole is 100 feet tall and it's bending in the wind, the middle of the pole has to be the most elastic. The bottom of the pole has to be the most solid. And the top is really there just to keep growing and bringing the plant more nutrients. So we've become interested in many species, but specifically in tropical species that are quite woody. So if you look at the figure on the left, this is out of Oscar Lopez's, a late Colombian architect, and I would say the grandfather of architectural bamboo. This figure shows the kind of, just in this case, 4 different species. And if you notice each section, the amount of woodiness from one to another is quite different. And so we're most interested in the most woody of species. However, as we try to adapt some of our ideas to more context, we realize we have to sort of open up our testing to species that might be, in some cases, more hollow. Also, if you notice the image next to it, there's 1,000 species roughly of bamboo, all different forms and textures and colors as they grow. But also, if you see the one on the far left here, this one I'm hiding with the cursor, many of these species have mutated over time and have quite different taxonomy. So just an amazing plant. The next image is in Thailand. This is giant bamboo. It grows, I'm told, up to a foot in diameter. It also grows, several inches thick, even though it's a hollow species. And then next is Madaki, a pretty common Japanese species. The next image after that is just showing these are all different species. This is not, from top to bottom of a pole these are cut from. It literally grows in all these different kinds of sizes. And again, it can grow, 100 feet long. And by the way, it might grow 100 feet long in 3 months. It can shoot a meter a day or more. So although I teach mostly industrial design, my interest kind of is, I think, pretty squarely positioned between architecture and industrial design. And I think in the areas of biomaterials, often I think industrial design, which has less constraints, is a pretty fertile ground to look for early folks developing interesting ideas. And so if you take the bike on the far left, James Wolfe, an industrial designer, designed a really high performance bike. It uses carbon fiber, automotive finishes, and this Vietnamese species that I'll talk more about in a future slide. Or the image next to it, really trying to kind of celebrate what was once a plant and how it might relate to a human. Or Lance Rake's sort of ingenious ways to take craft histories of things like barrel making and incorporate bamboo as a material system. Or this collaboration between an artisan and a designer using the kinds of processes used in making things like baskets that you might, boil a dumpling in. So I think in design, there's been a really interesting use of bamboo already. Of course, there's always room for more. In architecture, however, I think the investigations are somewhat more limited in terms of the way they might reinterpret the vernacular quality of bamboo. So on the far left, a Japanese kind of engineering project, research project, developing composite bamboo. It's rendered bamboo somewhat like sausage, no longer to have its full biological potential. In my mind, if possible, this should be avoided because, of course, nature has grown this wonderful thing. Why not extract as much of that potential out of it in its next life as a building part? If you look at the other work here, this Shanghai pavilion or the work in Bali, both are quite extraordinary, but I would argue they don't advance the way that we see bamboo. As we know, in many cultures, buildings have become flatter and squarer and more cementitious. How do we develop vernaculars that relate to those newer ideas about what buildings might be in a way that allows humans to accept these architectures, not as pavilions and not as sort of $1 million weekend homes, but as common architecture, as common building. So it's also important with bamboo to know that largely, unlike lumber products, other forest products, it's still worked in a way that's almost like pre-industrial revolution. So often the carpenter is the farmer. So the carpenter goes to the field, might care for the poles, but certainly is the one selecting and picking the poles and curing them and drying them and so on. And so because we're in Virginia, not in Vietnam, we didn't do any of those steps, but we sort of paid a penance for that. And so I wanted to sort of describe our process, which is I went to Vietnam. I met with James Wolfe. I learned quite a bit about this species called Dendrocalamus strictus, and observed his process. So they select poles, they heat them over a fire to straighten them because they grow bent when they're a clumping species like the one we're speaking about. Then they're soaked in a tank of boric acid, which is basically detergent at a high temperature to drive the sugar out of the bamboo for 48 hours. And then they're dried in the sun, often for a month or more, depending on whether it's the rainy season or not. And then in our case, they packed them into a container. That was wonderful. We wound up with this huge lot of bamboo to experiment with, but it came at a certain price too. University labs are not accustomed to container deliveries, for example. Also, I had no idea how much mold could grow in roughly 20 days at sea. Literally, it rains in the container. So it showed up to our lab. We have very kind of strict in the United States sort of, health requirements. And so we had to think about how do we how do we deal with this material? Can we even use it? So I learned quickly that it wasn't such a big deal, but we had to clean each piece before we thought it was good to bring it inside. And in a way, that's the penance we paid for not selecting it in the field ourselves. But the other important thing is we got to know the bamboo in a new way, touching the material, building tacit knowledge, not just for how to work with it, but literally what it is, what is its form. And then finally, we began to work with it in the lab. You know, bamboo is able to be unitized as a commodity, but it is not unitized like lumber. Every piece is different. So you really can't stack it the same way. You can't describe it with the same precision in a static way. So we've started to build some machines to process bamboo, to experiment with the intersection of technology and biology, and to develop machines that would allow someone less skilled as an artisan to work bamboo precisely, and also perhaps tools that might mediate between a designer's intent and a maker's ability. So we've developed actually several versions of this machine we call the BCNC. The first version is on the left here. It didn't really do what we intended. It did cut bamboo and you could write your initials with it and things like that, but you couldn't make any real joints. And so these first two machines we made a few summers ago and over a couple of weeks using 3D printing technology and CNC routing and Arduinos and, you know, pretty simple stuff. And I took this one to Vietnam and tested it to think, oh, maybe it will work to do some kind of manufacturing. It turned out it was a very good conversation piece for James and I to talk about, but it wasn't really quite productive in the way that we might have hoped. And that led us to kind of continue thinking about what to do next. And so a couple of years later now, we now finally have, you know, a modestly working machine, still could use lots of improvements. And the goal is to develop an open source project that we would share the designs with freely around the world, and that can be produced with simple tools and basic kind of computer skills for under $1,000. And so that, I think that will be ready to release within a few more months. And it builds upon the work of many others, not so much with bamboo, but the DIY community that's been building machines over the last, largely in the last 10 years, but in some ways for the last 25 years. So the whole reason we would do this is we're trying to rethink the way you think about materials. So, you know, historically, we thought about sort of standard materials, you know, in the last 25 years that were rectangles, flat rectangles. How could you reprocess a flat rectangle to build a new kind of product or a new kind of architecture that had more expression and that was still kind of had an economy of production? So these new materials, they require a different kind of thinking. And so perhaps maybe you have to be more collaborative with the material, but also to know it, we've been developing methods to scan it, to actually build models of every pole. So we want to know each piece in a precise way in order to use it to its fullest potential. We've also been playing around with some other ideas. And we've also recently learned that what we thought was called Dendrocalamus strictus, iron bamboo, may in fact be Thyrostachys siameses. And so these species can be misidentified. It's another challenge for bamboo, is that degrade it and identify it is quite hard. And I mean, actually the person who sold us the material, James Wolfe, is considered a world expert, and he's actually not sure which species it is now. And I show this slide just to say that this material is incredibly interesting. It's not solid, but it's solid enough to do things like turn it into what looks like an extruded square, or to machine a full twist onto it over about a meter. So this project, we largely are trying to rethink the way the vernacular of bamboo works. Can you see it as a woody, solid thing, not as a hollow tube? Can you avoid the kind of what we would call the Gilligan's Island kind of tiki vernacular that it's so often associated with? You know, not a indigenous hut, you know, but a kind of a contemporary building system. And to do that, we thought, well, how, you know, could we begin to make some planarity out of these things, turn them more into rectangles than organic shapes? And how would that affect its performance? And so, you know, looking at the histories of wood and of bamboo, wood is commonly turned into boards, but it's big enough that you just lose the whole outside. It doesn't really matter. It's sort of, you know, reasonable to do that. Or bamboo, often it's used whole or it's flat, but really trying to salvage every bit of its potential just in a flat shape, which largely loses its structural potential. So we thought, what if we could do something in between or something a bit different? And so we worked on developing some methods to turn it into small boards. And so the biggest question we had was, would it still have, mechanical benefit? Would it still be reliable and strong? And so basically we developed a series of different, permutations for shape and for how we might bend pieces. We made a small sample set, 3 of each, not a whole lot. And then we also tried to sort of look at area and figure out where's the biggest area, the smallest area, and can we try to make those as average as possible so that when we break these things, we'll have the most evidence that, they're similar. And so we did, tension, hardness, and bending testing on this material. And what turns out is that, in the United States, a 2x4 is a very common building system. It's called, spruce SPF2, spruce pine or fir 2 is how you would call a 2x4. And so there's a lot of literature on the common strength of a bamboo pole for bending, And so we compared first 2x4s to bamboo poles. And it turns out that in the round, as well as with one side cut onto it, until you get down to much smaller areas and at least 3 cuts, it turns out that the bamboo is still stronger than a 2x4 and doesn't lose a whole lot of strength either, as long as the area, the section, the height, and the width stays somewhat constant. Also, this material behaved really well when you compared it to other materials like steel. So this is a steel channel. These illustrations are to scale. So if that's about 1.5 inch to 2 inch tall bamboo pole, that's a 2 inch tall channel. And so pretty remarkable performance. And now is a good time if there are any questions that I'll stop for a second for a question. Are there any questions yet?
Yes, we have 3 questions here on the chat of Zoom, but do you want me to make them now or at the end?
If they seem appropriate, either way is fine. I'm happy to answer 1 or 2 now if it makes sense.
Okay. Well, we have one that it's from a student that says, that elasticity that bamboo has is what architecture tries to mimic with skyscrapers so they can react to earth movements and wind, right?
Mm-hmm. It's true. Yeah, bamboo is incredibly good seismically, and there's some work I'll show towards the end from Colombia that at the scale of 2-scale housing, it's been shown to be far better than concrete. And I actually believe that there was some work done on a shake table in Guate in collaboration, I think with an El Salvadorian group using this method that I'm sure could be found. I don't know where in Guate it was done, but yes, bamboo seems to have very good properties this way. Also, the way that it absorbs these stresses is why it's so good for a bike too. Was there another one that we need to speak to?
Yeah, that we have 2 more, but in that line is that the question was, does the elasticity that bamboo naturally has, does it benefit the structural integrity of products or buildings done with it?
So we think that it will, but also it's a double-edged sword because, if it's too flexible, that can also be a problem, even if it's not for safety, for confidence or comfort. So I'm not an engineer, so I don't know the answer yet, but I think what we're trying to do is to leverage, the benefits of that and then stabilize bamboo through compositing to manage the fact that it is so flexible. So it's not a pure benefit. And so often when you compare bamboo to wood, depending on how you look at it, you could want one set of properties more than another without a doubt.
All right, thank you.
Okay.
We have, we had one and a couple more. One is, wouldn't the bamboo swell with the rain? Is there a way to prevent it from swelling?
So yeah, you have to keep it dry. And so most of the things we're doing are thinking about it being, not the most outer layer of the construction. If it were the most outer layer, you would want to put a roof over it. You'd want to seal it or paint it. Even when it's preserved, it's rather susceptible to both moisture and to UV exposure. So it's not generally with bamboo, you design structures that shade the structural elements that are also bamboo.
All right, thank you, Jonas. And the last one, it's about the sustainable fact. It says, although the plant itself is renewable, is it still considered sustainable if it has to be shipped all around the world since the growing conditions are not as favorable in most places?
That's a great question. So first off, with 1,000 species, there are woody species that will grow in most all of the world. Also, if you look at where the most need for building and construction, specifically housing, will be between now and 2050, and you look at the tropical belt where bamboo grows, they're almost perfectly placed on top of each other. So one could argue, like, why are Americans researching bamboo? Well, the answer is because global warming is going to affect all of us, right? Do I think that making a bamboo system for North America is a sure bet? No, I don't. Do I think that it might be? Absolutely. And that's why we're engaging in life cycle assessment right now. So we don't have the answer yet. It may turn out that it's not appropriate for the United States. It could turn out that it's not appropriate anywhere. We don't have the answer from our own research yet, but the conventional wisdom is that it's quite sustainable relative to other materials, that it grows so much faster than even timber that, you know, that some estimates say that in 500 years, the current rate of consumption, not even considering the rate of growth of humans on the planet, that we could outstrip the forest of wood. You know, bamboo does not fit that same time frame. It's much longer. So is it sustainable? I don't know yet, but we certainly hope so.
Yeah. All right. Thank you. That's all.
Yeah, I'll keep going. Some of these questions will probably come up again later. So just to show you a little bit more about how this species grows, it's really quite interesting. You think of bamboo as a hollow structure, and of course it is, but you know, this species is quite woody. And so we did a lot of work trying to understand this so that we could develop geometries that would use this characteristic. If we want it to stay woody looking, then we don't want to hit the middle of the pole when we machine it, for example. Other times we might choose to expose that, but then we have to think, where in the pole would we do that? And so, you know, the nodes are always in different places, the wall thicknesses change, and so on. So our real kind of goal of this project was to develop a library of joints, and then to kind of develop a generative logic that would allow a compromise between the actual bamboo that we would understand through scanning, you know, a catalog of parts, a desired kind of form, and then we would essentially compromise to what the biology was asking for and what tools and machines we could develop. So these tools and machines were developed in two ways. One was that, you know, BC and C we've developed. The other, so that we could start working immediately on the bamboo itself, was to develop methods on a more conventional machine to also machine bamboo. So the fixture you see in this image is literally one that just, it finds a theoretic center of the pole, allows us to cut the pole, and then attach these little end pieces that allow us to index the bamboo for future processing, which I'll show next. And so, you know, every step requires its own little tool or fixture. Some of these we're inventing, some of these are really the products of histories from woodworking, others from metalworking and machining. And so in this case, now we're able to 4-axis machine bamboo. On a 3-axis machine, we rotate the bamboo and use an angle gauge to define what position to machine in, so you can machine multiple positions on a single pole. And then we're also using, you know, photography to take photographs of poles that get turned into scans using grasshoppers. So we basically edge find the bamboo in the images, and then we turn that into a swept surface. And then therefore we have a reasonably accurate model of the pole as it actually is, you know, not as we imagine it to be. And so then we spent a lot of time just learning how to machine bamboo, you know, and you know, I'm not an expert machinist, and I'm certainly not an expert bamboo artisan either. And so many of these things, others might say were so obvious, but to us, it's, you know, we're learning as we go, and we've gotten quite a bit better at it, but it's taken a lot of trial and error, breaking lots of cutters and lots of bamboo. And so some of the work explored earlier was really just trying to understand vernacular potential. So how could we change the vernacular qualities of the bamboo by finishing it differently, by carving into it in new ways? And so we developed some kind of sketch models at full scale, little mock-ups of different kinds of conceptual joints. Some were really joints, some really weren't joints, and they were just, you know, kind of intersections of sorts. And then finally, after about 1.5 years, we figured out how to machine it reasonably well, and decided to also play around with finishes that would, in a way, protect it, but more importantly, create this artificial skin so that we expose the inside of the pole, you might have more expression. We made some a few small structures. We've made one, and we're currently working on 3 of 4 others that we have planned. If you're interested more in this work, you can look up an Acadia paper that I co-authored with my collaborators, Katie McDonald and Kyle Schumann, that talks all about kind of standardless materials. So the next project I'm going to share is the one I'm, to be honest, most excited about today, which is the development of what we call smart cross-laminated bamboo. We would call it maybe a little brother or cousin to cross-laminated timber, and also a bit like a SIP panel, which is a building system used in the United States to make really well insulated, lightweight buildings that tilt up with very few parts. And we're also currently investigating whether the system how it will compare to concrete block. So our life cycle assessment is comparing CMU to SCLB. So again, this was largely inspired by my trip to Vietnam, working with James, looking at this species that they call Trai Gai in Vietnam, and beginning to understand that even the hollow species in Vietnam that are tropical can be quite woody. And so how could you leverage that woodiness in yet another way? And so the concept we came up with, Katie, Kyle, myself, and Dan Heineman, who's an engineer here at Tech in Forest Products, was could we turn this line into a plane? Could we build kind of structural potential that would extend what a bamboo grass or stock would be as a panel or a wall? So just to kind of give some historical connection. So, this is work from Latin America mostly. I mean, this is actually Europe, but basically some of this idea of making a kind of a rigid panel has been part of architecture in Colombia for around 100 years. Only it's a site-built system, and it's limited to 2 stories. And the bamboo is not necessarily perfectly well known. So, it has its limitations. But to be honest, when we started, I didn't even know about this process. But I think it has quite a bit of similarity to what we're trying to do, which is to basically, take this incredible property and then extend it, as a plane. So we began by thinking about how we might break up bamboo poles to make them into planes. Do we leave them whole? Do we cut them in half? Do we use 1.5 poles or 2 poles in the system? Do we use 1 species or 2 species? And then how do we imagine bamboo poles could map into a panel and be graded? The different elements might need to be in different places. And the image on the right, it was my guess of what would make the strongest panel. It turns out I was wrong. My guess was quite wrong about what the best method would be to make the strongest panel to resist bending and failure. But the notion that you would grade the panel with parts that would be placed in just the right spot, so that instead of using a factor of safety based on the weakest piece, you wouldn't have to do that if you could put the right piece in the right place. Furthermore, could you somehow map that same kind of generative intelligence to the building itself? So could the bamboo pole, as it's standing in the field, as you cut it, could you decide where in the building it wants to live to fully express its mechanical structural potential? So to begin with, we just had to figure out how to fabricate these poles. And so lots of different fixtures and tools and machines were explored to kind of figure out how to machine bamboo into a flat board when it's anything but flat to start with. And you're trying to remove as little material as possible, but come to sections of wall that might have common thicknesses. So if you had a building, you probably wouldn't have every story with the same thickness of wall. Maybe for floors, you wouldn't either. A public floor might have a thicker floor than a private floor, for example. But we'd have to at least get to a point where we could make pieces of a few different thicknesses out of what is largely completely random material. We also wanted to democratize the way this could be done. So instead of needing a big factory, we developed methods and fixtures for gluing that would require very little expense. You wouldn't need a big industrial press. You would need a flat table and some threaded rod and a few nuts. And so we developed a series of panel tests of different permutations, experimenting slightly with grading of the different elements, and also different, kind of taxonomic relationships between skins and poles and half poles and pole turns on end or on angles and so on. And so here's just a couple examples of how we did that in different ways. And then here's a chance for somebody to give their opinion. So I already mentioned that this was not the strongest panel, but of these three, which one was the strongest? Does somebody want to take a guess? Anybody make a guess or not?
Left, they say.
Maybe the middle one.
We have the three options.
Yeah, so it's not the left one. So is it the middle or the right?
Middle, I think.
Middle.
Okay. So why is it the middle?
It conserved the shape, the roundness of the bamboo.
Exactly. And there's another reason why too. Is there anyone is there an engineer here by any chance? No engineers? All right. So the one on the left, I expected to be the strongest, but we used an inner layer, a woven inner layer, to help spread the glue. And there's a quality of bamboo called rolling shear, which not all materials experience when they're bent, but bamboo pretty easily goes into rolling shear. And so even though in this panel you have long grain glued together as far apart as possible, which in theory in other stress skin systems would make the strongest result, what happens is the mat in the middle slides and all three layers bend together, but they don't bend as one, they just bend together. So what happens in this one is exactly the same. The parts go into rolling shear, and you can see how this mat is wiggling in the panel when it's being bent, and then it flattens out when you take the stresses off. None of them broke. I mean, they all failed a little bit, but none of them catastrophically snapped in half. They all basically sprung back about 90% or more after the press was let off of them. But this one took twice as much to break, and I'll show you those numbers in a minute. We also added a few more tests to the mix. This one with no skins, as well as this one where we had the poles straight. And so we entered in, we took out the mats and we added in a second species. So now we're using iron bamboo and Tray Guy in the same panel. And in this panel here, where this one popped off under enough load, the panel was, these were on a 45-degree angle. The ones in the top were on the opposing 45-degree angle. And by the way, the reason these popped off was not mostly that the bending stresses caused it. It's because the students did a really poor job gluing. We had not defined a clear enough method for gluing yet. And so some of them actually fell off just by picking the panel up off the table when it was glued. So we knew they were going to fail. But what happened is these ones on a 45 acted a bit like an outside skin and held the middle of the panel together. So here's the results of these five panels in their bending tests. So the one with the 45 elements is the purple one. The blue one is the one that I asked on the first slide, which one was the strongest. And so in bending, these two outperformed all of them by a significant amount, and they doubled in the first three. The blue one doubled the strength just by changing direction. So this is not necessarily a slam dunk, an absolute fact yet, but what it's leading me to believe is that if you preserve the biological intelligence in the most obvious way, which is to leave the whole pole as whole as you can, run it the longest way through the panel, that has some benefit of doubling the strength of the same material organized another way. So we've also been playing around with growing and with plants and with fungus, and in many ways, some of these things are just early opportunities to have design students touching growth, even though we know this probably won't be particularly useful as a technology. So we took bamboo plants, we stick them in these little fixtures, and we grew them at different angles to see if we could influence the growth, the longitudinal section. Could we basically program the growth of a line? And we're not the first ones to do this. Brian Erickson, who's a bamboo enthusiast in Costa Rica, and Oscar Lopez in Colombia, both did something similar, but they didn't do it with moving the plants. They just pulled on the pole. They used mechanical forces to train the plant. And we thought, well, that's really cool, but you don't have you don't have that much control that way. What if we could just use the orientation of the sun to control it? And it definitely worked. But then as we learned more about bamboo, we learned that the rhizome requires not just one shoot to be growing at a time, but 2 or 3, because the plant from the year before is what actually feeds the new plant. So it might work in a lab, but it would never work at scale. But what it did was it got us thinking about, oh, we really need to know more about growing the bamboo as part of our process. We've also been working with some folks from UC San Diego, a biologist named Stephen Mayfield, and a few chemists that he works with, at using algae oil, polyurethanes made from algae oil as an adhesive system. If we're trying to make a green product using petroleum-based glues, seems like not the best idea. However, currently there aren't a whole lot of other options. So Stephen's lab has developed polyurethanes that are designed to biodegrade not into microplastics, but back down into organic material. And they're made, eventually they'll be made 100% from algae in a tank, which is not that much different than oil, except it didn't take 1,000 years in the ground to be produced. It took a few weeks. So we've been testing these glues to see if they perform, and they perform just as well as the other glues we've used. So basically they've actually performed slightly better. So they have a little bit better elongation than the other glues we've used. And so on a purely mechanical level, we could make the shifts. These glues are not fire rated yet. There's plenty of issues we still have to work out, but we're encouraged to think that we might be able to use these glues as a replacement. And although they're not made from petroleum, they're still a heavily processed chemical. So maybe it's still not the perfect solution, but it may be better than anything else we had yet. And so we're also trying to develop some further investigations. And so I've recruited a mushroom farmer. He was an art student in undergraduate school and became a mushroom farmer, an amateur mycologist. And I recruited him to graduate school in our program. And we're studying if we could use the roots of mushrooms, mycelium, which is already a known building material in a mild way, in a packaging material. Could we use it as a way to assemble a panel? So we haven't done a whole lot of work yet, but we've begun to do a little bit of experimentation with trying to just composite bamboo particles and sawdust that have been inoculated with oyster mushroom mycelium and reishi mushroom mycelium to develop kind of composite panels. And so our long-term goal is to try to make a fully grown system, whatever that might mean. At this point, it's still just a metaphor, but that's sort of, in many ways, the goal of our lab is to really, everywhere you can, leverage biology, whether that's by literally using biology or that's by using, biology as inspiration. We think in both cases, this is the kind of future of how we might live more symbiotically with the rest of the planet. So we're currently working on a couple projects this summer and hopefully some over the next 2 years. The 2 projects on the top right we'll build this summer. Actually, the blue one we're building right now in the lab. It's just a small little kind of playful structure that's trying to build a generative potential for using the bamboo intersections, not driven by an original idea for form and repetition, but actually letting the form modify to wherever a node or internode is. So that's currently under construction right now. This summer, we're going to build a ceiling for a dorm building. We're also playing around with lime plaster, some of which we're buying, but some of which we're actually going to make from the quarry dust from a local quarry, stone quarry. And then finally, we're beginning to build a kind of prototype out of the CLV system as well. And then I hope in the next 2 years to be building some kind of building in both Vietnam with James Wolfe and in Guatemala with Alfredo and Roberto. And we hope to be making kind of small, temporary housing prototypes, begin to understand how these ideas might work. And we're also going to have to shift species. I'm sure we'll use Guadua mainly if we work in Guatemala. So some of the assumptions about solidity will have to be questioned and re-examined. And we're currently beginning to do that work now. So, this is kind of, where I'll start to just take questions. And also here's a link to my email, another one to our website. And I would encourage, your 5th year seniors and 4th year, if it's ID, I guess, if they're interested in, school in the States, we're actively recruiting MS students to our program. They're interested in biology and technology, at various scales. The cohort this year will be about 8, and we hope to keep growing that, you know, myself and a few colleagues. So I'll just leave it there for questions. And then, you know, after that, I have a little surprise, but we'll have to stop broadcasting before we get there.
Yeah, we have one last question here, Jonas. When you were presenting the panels, it was, do you think that this cross-laminated bamboo can be used with concrete? Or do you think it will be the most successful by keeping it all the structure with bamboo?
So you know, what we know more and more is that steel and concrete, because of embodied energy and extraction, are terrible for the environment. So if you said to me, do I think that we can build without concrete right now? No. I mean, foundations, there's still no better solution for a foundation that humans have come up with than concrete, than masonry, right? But if you said, do I think that we should use a lot less concrete? I would say yes. Do I think that you can marry bamboo and concrete? Yes, there's many examples already, including that work from Colombia that I shared. What I'd like to propose, though, is that we start thinking about, you know, what is either pre-concrete or concrete 2.0. And they're actually maybe in some cases the same. Lime plaster was used for thousands of years before we ever, you know, industrialized concrete or cement, more importantly. And lime plaster, I think, is a far more sustainable solution. I'm not an expert in it, even less so than I am with bamboo, but we're trying to explore whether or not lime plaster can become the cementitious coating, over the lath of the bamboo panel that would give it UV protection. It would give it, moisture protection, and maybe equally importantly, is it would provide the vernacular that many expect for a concrete-like building system. So in my mind, the answer is yes, but you have to think about that metaphorically. You know, what is concrete in the non-literal sense?
Yeah, thank you.
Sure.
We have 2 more new questions here. One is, how far is bamboo from being an option that developers can consider based on economical viability?
That's a really good question. And I would refer to the work of David Trujillo, also a Colombian engineer who now practices or teaches at I think it's, he's in the UK. I think it's at Bath University, at Bath. The work of his, you should also look at INBAR, which is the kind of World Bamboo Organization, it's a global bamboo organization, or the World Bamboo Organization as well. For some of that information, there are some life cycle assessments, mostly with MOSO, but I can't answer that question across the board. It's better if you look at the literature for that answer.
All right, thank you. We have other 2. What can be done so that bamboo structures do not have problems such as heat and cold inside the house or structure? Do you use a solution with natural elements?
So I think that let me go back to the slide that shows that method. It's probably the easiest way. So, you know, this historical method, you are making a hermetically sealed building with concrete and bamboo. I mean, in my mind, that's the answer. Are you still going to use glazing? Yes. Are you still going to use a concrete foundation? Yes. But there's already, at least at the scale of residential architecture, you know, a very good example that has been pretty well researched and tested over, 100 years. And, you know, if you look into Colombian bamboo, you'll learn lots about this. It's definitely been done in other parts of Latin America, but I think the Colombians are by far the most experienced with it and the best place to look for it. So that would be my answer to that question. And if you asked how our system is going to do that, it will do it in a similar way. You'll tile together panels. Those panels will get mortared over, I hope, with lime plaster if it works. You'll still use common windows and so on. So I think, like any other, building system, it will be an aggregation of elements. The building product of a bamboo panel plus other building products like windows and doors.
All right, and we have one last question and one comment from Facebook before we stop the live. But the last question is, what do you think about the aesthetic qualities of the material? What kind of architecture do you envision for the future of bamboo construction?
So I think that there's when we started this, our goal was to really develop a new formal aesthetic that did not, that did not feel like a tiki bamboo hut. But as I've learned more, both about what other practitioners have been doing, and I've learned to love bamboo more, I think that I don't see it as much of a disruption as I originally did. I originally thought, oh, we want to disrupt this idea of what it was. And now I feel like we just want to work with it in lots of different ways. And I don't think there's a singular stylistic position to take. And at least in the work that we're doing, I do think that exposing more of the expressive possibility of the material is quite useful. And then to balance that against things like, fire protection, or UV and moisture and rot, those are going to be the challenges. There's no doubt in my mind, whether it's full poles, in a sunscreen, or the milled poles we're making, it can be quite beautiful, even in a contemporary sense. It's just how do you preserve that while also making for a reliable building system? And these are great questions that I think, that's the call we make to everyone else is, don't ask us, tell us, let's start doing it, right?
Yeah. Well, thank you.